there are two different factors that affect how labile a coordination complex is. The lability of the coordination complex will tell us whether the dissociative mechanism is preferred or the associative mechanism. So if a compound is labile, a ligand will pop off, and that will favor the dissociative mechanism. However, if the compounds are inert, that means the formation of a bond between the ligand and the metal cation is preferred, suggesting the associative mechanism. We will look at how rate constants are affected by different experiments, but we need to know two factors that affect the lability of a coordination compound. First is the charge on the cation. If you increase the charge on the cation, that leads to stronger interactions between the cation and the ligand. If there's stronger interactions, stronger bonds between the cation and the ligand, this decreases the lability of the compound. Second is the size of the cation. If you increase the size of the cation, that means there will be smaller or weaker interactions between the cation and the ligand. That means the bonds are weaker, and bigger cations form more labile compounds. We can combine these two ideas into one criteria called charge density. Charge density is the combination of cation size and cation charge. As the charge density is defined as dividing the charge on the cation by its radius. As the charge density increases, the charge of the cation increases while its radius decreases. As the charge density increases, the strength of the metal ligand bonds increase, and the complex becomes more kinetically stable or inert. So let's look at some data for the reaction for the water exchange reaction. Remember, we're exchanging radio-labeled water with non-radio-labeled water. And we're going to look at how labile the compounds are, and look at and try to make some try to draw some conclusions from this data. So what you're looking at in this graph is on the x-axis is the logarithm of the rate constant. If the logarithm of the rate constant is 0 or greater, the compound is classified as labile. If the log of the rate constant is less than 0, it is classified as inert. First, let's look at metal cations that all have the same charge but different sizes. So when we look at this group, this is the alkali earth metal cations: lithium, sodium, potassium, and cesium. As you go down the group, notice that the rate constant increases as the cation gets larger. That means that the metal complex becomes more labile. Lithium 1+, when surrounded by 6 waters, is not as reactive as cesium 1+, surrounded by 6 waters. Second, remember we need to look at how the charges on cations affect their lability. So we need to choose the same atom with different charges. Fe2+ has a log of the rate constant equal to about 6. If you come down and find Fe3+, the log of its rate constant is about 2. Fe3+ is less labile than Fe2+. suggesting that higher charge leads to more stability and less reactivity. You can also see that with cobalt 2+, which has a log of the rate constant equal to about 6. Cobalt 3+ is considered inert and has a rate constant of about 10, a log of the rate constant equal to about -2. You can also look at chromium. Cr2+ has a log of the rate constant equal to about 9, but Cr3+ is clearly inert, with a log of its rate constant being 10 to the -6th. So that data supports that this is a dissociative mechanism that substitution reactions occur by. We need more data to support this idea. We can use annation reactions to think about this as well. An annation reaction is a reaction where a ligand in a coordination compound is replaced by an anion. For example, if we take a metal compound or a coordination compound that has 6 water ligands and react it with an anion, X-, the resulting coordination compound would be MH2O5X. The charge on the complex cation must be reduced by 1, and you must have a water that is no longer bonded to the metal. Much like ligand exchange reactions that we just looked at, annation reactions also seem to proceed by a dissociative mechanism. It seems that it does not matter what the anion is, that the rate of the reaction is dependent upon the breaking of the metal-water bond. The data in this slide supports this idea. In this table, we are looking at the rate constants for substitutions of NiH2O6 In the first 3 pieces of data, we have 3 anions, the ligand that will come in and replace one of the waters, F-, SCN-, and CH3COO-. When we look at the log of the rate constant, they are all about the same, between 3.8 and 4.3. This suggests that it is the breaking of the water-nickel bond that controls the rate of the reaction, not what type of ligand replaces it. We can also check this with neutral ligands, such as NH3 and radio-labeled water. Notice that the log of their rate constants are about the same as for the replacement of water with an anion. All this data also suggests that annation reactions occur by dissociative mechanisms. Aquation reactions are next. This is where a water molecule replaces another ligand in a complex. In this complex, L is the ligand that will be displaced, and water will come in and replace it. Now the ligand can be anionic or neutral. If it's anionic, the charge on the resulting complex will increase by 1. Now the rate at which anionic ligands are exchanged with water molecules in inert pentaamine ligand cobalt 3 compounds were extensively studied. That data will be used to determine if this goes by an associative mechanism or a dissociative mechanism.